Welcome to Spring LIB.
In this exercise, we're going to be talking about circular motion. So before solving the problem, I'm going to give a brief review. So when talking about circular motion, we're talking about a particle that is undergoing a circular orbit, just like this one here. And we can decompose the particle's acceleration into two components. One component that is centripetal, that points towards the center of rotation. Okay, this is the centripetal acceleration. And another component that is tangential, which means that it's tangential to the curve made by the trajectory. And these accelerations are such that the centripetal acceleration accounts for the change in direction of the velocity, even if the velocity itself, the magnitude of the velocity doesn't change, and the centripetal acceleration is equal to v squared divided by r. The tangential acceleration, on the other hand, accounts for the change in the magnitude of the velocity, that is, the change in speed. And these two informations is what we need in order to solve the exercise. So what we have is a boy in a swing. The boy has a mass of 60 pounds, and when theta here in the figure is equal to 60 degrees, the speed v0 of the boy is equal to 15 feet per second. And the length of the swing, and hence the length of the radius of the orbit of the boy, is 10 feet. And our goal is to find both the rate of increase, that is the vdt, of the boy's speed, and the tension in each of the cables that connect the buoy to the center of rotation. So notice that if we look the buoy from the front, there are two cables, and each one is exerting a tension T on the buoy, and also there's a force acting downwards that is just the force of gravity. So let me draw the force diagram a little differently. Here I drew it from the perspective of someone who is in front of the buoy, but I think it will be a little better if I drew it from this perspective. So there are 2 times T, the force of two tensions, acting radially towards the center of rotation, and there's also the gravity force acting downwards. And my goal is to decompose the total force into two components, one that is perpendicular to the one that is tangential, I'm sorry, and the other one that is centripetal. So what I'm going to do is realize that if this angle here is theta, then this angle here is also theta. And in order to decompose the forces into a tangential and a centripetal component, what I'm going to do is to use that this angle here is theta. Okay, so notice that in the centripetal direction, in the radial direction, so I'm going to call it R, we have the forces 2T minus mg times the sine of theta, and this is equal to the mass times the centripetal acceleration, which we saw it is v squared over r. Then in the tangential direction, which I'm going to call theta, we only have mg cosine theta, and this is equal to m times the tangential acceleration. So if we want to find the tangential acceleration, we use the equation for theta, so we have that at is g times cosine of theta. So at is 9.8 meters per second squared times the cosine of 60. Now, instead of writing the gravitational acceleration in meters per second squared, since the exercise is talking in imperial units, I'm going to use the acceleration in feet per second squared, which is 32.2 feet per second squared. This is the gravity's acceleration, meaning that the tangential acceleration is 16.1 feet per second squared. Okay, so this is the answer to the first part of the exercise. And in the second part, we have to find what is the tension on the string. So I'm going to use the equation for R. So I'm going to copy it here. So we have 2t minus mg sine theta is equal to mv squared over R. Now, at the time when theta is equal to 60, v is equal to v0, which is 15 feet per second. So t is equal to m divided by 2 times g sine of theta plus v0 squared over r. Now m is 60 pounds, g is 32.2 feet per second squared. Then we have to multiply by the sine of 60 plus 15 feet per second, all of this squared divided by r, which is equal to 10 feet. Now the answer will be in pounds times feet per second squared. Now we know that 1 pound force is equal to 32.2 pounds times feet per second squared. So what I'm going to do is divide our result by 32.2 pounds feet per second squared per pound force. So we obtain that T is equal to 46.9 pound force, which concludes our exercise.